Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this lesson, we're going to look at Year 2 content, looking at the rate equation. We're going to look at the rate constant K and the orders with respect to each of the reactants within a rate equation. In terms of how this links with Year 1 content, it would be important for you to go back and watch the video on rates of reaction and how we measure rates of reaction, if you haven't already recently. So imagine we have a reaction where the two reactants A and B react together to form the product C. So our rate of reaction is how fast A and B as reactants get converted into the product C. And we can either track this with the reduction of A and B, so their concentration decreasing, or we can look at an increase in C. And so we monitor a property that is intrinsic to either A, B, or C. And as this property changes, we can determine some information about the rate of reaction. So we can plot how the concentration of, for example, A decreases over time, and this is called a concentration time graph. And so if, for example, we're tracking a reactant, at the very beginning of the reaction, the concentration will be its highest, and then over time, it will decrease as it gets used up. Now, in the opposite way, the concentration or the property of C, at the beginning, there will be no C because no products have been formed. And over time, this would increase. And we can come up with an initial rate of reaction. So this is the rate where time is roughly 0. So it's just started the reaction. So you can draw a tangent line at roughly this area. And this will give you your gradient for the initial rate of reaction. And just to reiterate, this is from the concentration time graph by calculating the gradient of the tangent at time 0. So what I did was draw this tangent line up to the curve at time 0, which is roughly here on the x-axis, and that gives us our initial rate of reaction. And you'd use this to calculate change in y over change in x, and because we've really extended our tangent line here, this makes this job really easy. Again, we've been through this in the Year 1 video of rates of reaction in the Module 3 playlist. So our change in x is going to be where the tangent line bisects the x-axis up to 0. And then our change in y is where we have the tangent line again bisecting the y-axis down to 0. And so whatever these values are, you divide over and you would get your initial rate of reaction. So it's important that the overall rate of reaction can be determined by the initial rate method, which is taking a tangent at time 0. But what's really important is that the overall rate of reaction is determined by the relationship that each of the reactants has on the overall rate. And this leads to a really important relationship. And this relationship is known as the rate equation. So the rate equation, it's really an equation that's telling you how the rate is affected by each of the reactants, and specifically the concentrations of the reactants. So as we change the concentration of a reactant, how does that affect the rate of reaction? So our rate equation starts with rate, and this is the rate that you would measure using an initial rate method or some other sort of method that we'll see in later videos. And that is linked to the reactants by a Firstly, a constant called K, which is lowercase k. It's known as the rate constant. We will see later that its units are dependent on the reactants and to which power or order that they are to. And as I said, we will be talking about orders later on. And then depending on the reactants, so if we take our example here of A and B going to C, our reactants can appear in the rate equation, and they will always be in their concentration, so concentration of A, and this is denoted by the square brackets, which means mole per decimeter cubed. And then also the concentration of the other reactant, B. Now at this point, it's important to note that your reactants A and B, in this case here, might not have exactly the same effect as one another on the rate. And that goes to say in any type of equation. And so we raise the reactant's concentration to a power. We call this power, here shown as X and Y, as the order of reaction, and that is with respect to each individual reactant. Now at A level, these orders of the reaction with respect to each reactant can either be 0, which is 0 order, 1, which is first order, so that means whatever your value of concentration is, you just times to the power of 1. And then finally, it can be second order, which is where X or Y would be 2. And so you square the effect of the reactant. So let's just look at our reaction A plus B going to C. Our two reactants are here, and they therefore could appear in the rate equation. The rate equation can only ever show the reactants in there. You never include the products in the rate equation. Let's just focus in on the reactant A. We're going to do a series of hypothetical experiments and work out the order for A. So firstly, we're going to just run the experiment A plus B going to C. We're going to keep the concentration of B as a control variable, so we're going to keep that fixed. And what we're going to do is run an experiment where the concentration of A initially is also 1 moles per decimeter cubed. So we run this experiment and we continuously monitor it, so we get a concentration time graph. And we can see this graph here. Then we're going to use an initial rates method, so we're going to take the tangent at time 0, and then that allows us to generate a rate through this initial rates method. And just for our hypothetical case, imagine we've got worked out a rate of 0.5 moles per decimeter cubed per second. So we're going to run the same experiment, A plus B going to C, but this time the concentration of A we're going to double to 2 moles per decimeter cubed. So this is our independent variable. As I'm sure you're aware, if we change one variable, it means we have to keep everything else exactly the same. So we are going to keep B, the concentration of B, as 1 mole per decimeter minus 3. And again, we allow the reaction to occur. We take a graph, we take the initial rate method, and we get a rate from it. And in this case, the initial rate we've worked out is 1 mole per decimeter cubed per second. So what we've realised here is that as we double the concentration of A, and you can see this, we've gone from 1 mole to 2 mole, the rate has also doubled, going from 0.5 to 1 mole. So if we're to simplify this rate equation just to the two things, the dependent variable, the rate that we've been measuring, and our independent variable, the reactant A that we have been changing its concentration, then what we can simplify this as is the concentration of A is proportional to the rate. So when we've doubled A, we have doubled the rate. Or you could think that whatever you do to the concentration of A is to the power of 1, how it affects the rate. And so we know that A is first order. The phrase to use here is the rate of reaction is first order with respect to, that's what this WRT designates, concentration of A. Now obviously this is only allowing us this set of experiments to work out the effect A has on the rate. We would then have to go back to our rate equation and work out the effect that B has on the rate using the same principle. But this time, B would be the independent variable and A would be a control variable with the concentration set over every experiment that you run. Now we're going to look at how the data would look for different types of orders of reactants. So 0, first and second order. Imagine we've got the reaction again of A and B reacting to form C. Now we're going to just isolate and focus in on one of these reactants, A, and this is what these columns here are going to be showing, the concentration of A. And in each experiment, what the scientist has done is change the concentration of A whilst leaving B exactly the same as a control variable. And then what they've measured is in this column here. This is their dependent variable. They've measured the initial rate by using the initial rates method and a concentration time graph and taking the tangent at time 0. So you can see here IV for independent variable and DV for dependent variable using the initial rates method. So what has happened here is in experiment 1 to 2, then we've doubled the concentration of A. Then what we want to do is consult how has the initial rate, our rate of reaction, changed if we've doubled A. Well, you can see here, comparing experiment 1 and 2 together, nothing has changed. So what that is like is whatever the concentration of A is, it has no effect on the rate. So no matter what the value of A is, it is times to the power of 0, which makes it void, makes it totally irrelevant. And so if I was asked to construct a rate equation at this point, then I know rate equals K times whatever the concentration of A is to the power of 0. Now I don't know what the effect B is at this stage, and so I'd just leave that as B to the power of Y. I'd have to do further investigation there. But what I can do is, because A is to the power of 0, it doesn't matter what the value of A is, so I can simplify my rate equation further. I do this by removing A to give me rate equals K to B to the power of Y. So let's change our data set here. So we're looking at the same reaction, A plus B going to C, but this time in a totally new situation. So what we've done is, again, we've doubled from experiment 1 to 2, we've doubled the concentration of A. So we've changed that. And what we've noticed is the initial rate has also doubled. So in this case, as we've increased A by 2, then the rate has also proportionally increased. And in this case, it's directly proportional. So we know that whatever we do to A, it gets emulated on the other side of the equation to affect rate. And we show this by doing it to the power of 1. Again, we'd have to do further work to work out what the effect of reactant B is. And so that's our rate equation at the moment. Now it's important to note that whenever you do something to the power of 1, you don't need to show that you're doing to the power of 1. So this would simplify even further as the following. And in our final set of data, we're going to imagine we're dealing with A plus B, where A is actually in this situation second order. So if we look at this data, you can see that as we have doubled the amount of A, what's happened to the initial rate is that it has quadrupled, times by 4. Or, even better to think about, is it has doubled to the power of 2. So 2 to the power of 2 is 4, and that is what has happened to our data going from here, experiment 1 to experiment 2. And so this makes our rate equation totally different from the other two scenarios, as its rate equals Ka to the power of 2, so it's second order in this case, whereas we had 0 and first in the other cases. And again, we don't know until we do further calculations what the effect b has on the rate, so we're just going to keep this b to the power of y. So imagine that we're keeping with that final data table and that we've worked out that rate is a is second order, so to the power of 2. And then we did further experiments, this time keeping a completely the same as the control variable and changing b, and worked out that b was first order. So individually, we know that a is second order and b is first order. And what we do is we use these to come up with an overall order of reactants. This is basically the sum of all the orders for each of the reactants individually combined together. So here, because it's second order for A and first order with respect for B, then the overall order is third order. So far we've been using the idea of rate of reaction. We've looked at order of each of the reactants individually, putting them together to give you an overall order. We've touched on the rate constant K, and we're going to use this in a moment and look at this in more detail. Half-life and rate determining step we are not going to be looking at in this video, but later in other videos. We've looked at deducing a rate equation from orders. And now what we're going to do is look at calculating the rate constant K from a rate equation. So take into consideration this reaction here where we've got nitrogen monoxide reacting with carbon monoxide and oxygen to form NO2 and carbon dioxide. Now, the rate equation is going to show the reactants and the order to which that they affect the rate of reaction. And you can see here that it's second order with respect to this reactant, NO, and the fact that CO and O2 do not appear in the rate equation shows that it's zero order with respect to each of these. So these have no influence on the overall rate, whereas there's a second order influence of NO on the rate. If we're told some information about when a scientist had ran the experiment of this with 2 times 10 to the minus 3 moles per decimeter cubed of the nitrogen oxide, and when they measured the rate of reaction for this, they got 1.76 times 10 to the minus 3 moles per decimeter cubed per second. So we've been given NO data, we've been given an initial rate, and so we can rearrange this to get K. And so if we take the NO over the equation, then we get rate divided by NO squared. And then what we do is we sub in the values, so rate and the NO concentration, and then this gives us our magnitude, our size for the rate constant. What then remains is that we need to work out the units for K. Now it's important to always remember the units for rate is always going to be moles per decimeter cubed over the time that you're looking at. So in this case, our units are moles per decimeter over seconds. On the other hand, concentration, square brackets, is always moles per decimeter cubed. And so we can put those units into the equation that we've just rearranged up here. Remembering that the concentration is squared, we can express this further. And then what we want to do is cancel out the units where appropriate. So we're left with only S minus 1 on the top there. We've cancelled out one of the moles on the bottom, and we've cancelled out a dm minus 3 on the bottom. So we're left with this. And we want to get rid of the fraction. So we're going to use the index laws to get us to put this on top line. It becomes mole minus 1. dm was minus 3 on the bottom of the fraction, so it's now cubed on the top because all the signage changes, and then S minus 1 stays the same. So what we've done there is we've determined our units for K and also our magnitude for K. Let's put some of this into practice, looking at an exam question. So this is a free marker, and what I want you to do is pause the video now and attempt to calculate the rate constant K for this reaction using the information that's given in the question. Okay, so if your answer was 8.3 times 10 to the power of 4, and your units are dm6 mole minus 2 s minus 1, then you've got all 3 marks available. If you didn't, don't worry, we're going to go through the answer right now. So we've been given the rate equation there, and we're being asked to work out what K is. Now, in terms of some of the data that you've been given the initial rate as 3.6 times 10 to the minus 2, so that's our rate, this part of the equation. And we've been given concentrations given by the units here. For hydrogen, we've been given 1.2 times 10 to the minus 2, and for the nitrogen monoxide, we've been given the 6 times 10 to the minus 3. So all we've got to do is rearrange this equation to make K the term. So keeping K on the right-hand side and then moving the 2 concentration terms and the power over to the left-hand side, we get this equation here. And all we then need to do is input and substitute in these concentrations into the correct areas. And then when you put that into your calculator, being careful to include the squared and these values in brackets. Remember, really careful, because if you're ever doing anything to standard form, put it in brackets. It just saves your calculator any silly mistakes. That should then give you this value here, whether in standard form. And then units wise, well, the mole per decimeter minus 3 cancels the moles per decimeter minus 3 here. Left with S minus 1 on the top, and on the bottom we're left with our squared units at the bottom here. And again, to remove the fraction, we're going to place these on the top of the fraction, and in doing so the signage here changes, so this becomes minus 2 and this becomes just 6, leading to the units here, which gives us our final mark. And so I hope you've enjoyed this lesson on the rate equation. It's fundamental for the rest of the rates topic, so it's really key that you get your head around the key concepts around the rate equation, the orders of reactants, etc. If this video has been useful, ensure that you like it, ensure that you subscribe to the channel so that you can get updates on all the other videos as they come for A-level chemistry.